Welcome everyone to this seminar series of mathematics and high energy physics by Physics Latam. Today we are very happy to have Professor Artan Sheshmani. He is currently professor at CMSA at Harvard University and professor at BIMSA, an institute part of Tsinghua University. He is also part of the Simon collaboration in homological mirror symmetry. His interest lies mainly in algebraic geometry and emergent geometry, especially on Gromov-Witten theory, Donaldson-Thomas theory, mirror symmetry, derived algebraic geometry, and mathematics of string theory. And today he will talk about super Gromov-Witten invariants and almost Kähler varieties. Thank you very much for accepting the invitation.
Thank you so much, Daniel. Thanks for inviting me to your talk. Just a quick correction that actually I have recently moved to a joint institute between Harvard and MIT, which is IFI Institute. But anyways, it's almost the same. Yeah, so I'm going to talk about super Gromov-Witten invariants on almost Kähler varieties. This is a joint work I did with my former postdoc, Enno Kessler, who was in fact being, he was a postdoc who was working with me under supervision of me and Professor Yao at CMSA. And nowadays, Enno is in Max Planck Institute in Bonn. And we have written several papers on this. I will tell you very rough picture. What is the story? And the work I'm actually describing today in the form of a 2-hour lecture is about actually some of the work which has not yet appeared on archives. So I thought that maybe why not? I can just focus on the newest things that we have been exploring on this very topic. Okay, so let me tell you. So I think majority of people in here are mathematicians and physicists. So I don't need to really go through too much of the preliminary background, but here is, I just draw for you one picture before starting my talk. So imagine that this is our space-time. You have particles. In quantum mechanics, you have particles, and Feynman actually tells you that particles come and interact with each other. So you have these Feynman diagrams and things like that. These are actually capturing all possible ways that particles can get interactions. And the result of interaction between particles, let's say if you want to actually calculate energy of interaction between particles, is a Feynman path integral. So you have the Feynman path integral. That's a good suggestion. That's a good suggestion. I never actually thought this is okay, never did it before. Okay, so you're doing Feynman path integral, and you're calculating energy of the particle. In general, in quantum mechanics, in classical mechanics, you have a particle of some given mass going from some point A to point B. You want to calculate energy of this particle. It's an integral over the path. So this is the path. Here's the path. It's a, let's say here it's a curve, some measure. So you put some integrand. Integrand is giving you a measure, whatever it is you're integrating. Maybe it is a force field, and in calculus, force is moving the particle. So you do F dot, for instance, D of S. You parameterize the path, you look at the inner product and kind of calculate dot product and calculate. So that's what energy of the particle in classical mechanics. In quantum mechanics, pictures like I drew above, particles come together in many possible ways. And so to go from one A to B, roughly speaking, your particle can take many possible paths to go progress from a state A to a state B. We are not necessarily actually talking about paths in the space-time, but it is possible that you look at the path that the state of the particle traverses in the space that parameterizes the states of the particle, let's say some Hilbert space. But nevertheless, it's a certain path, whether it is in the status space or in geometrical space. The point is that quantum mechanics is about uncertainty, and particle progresses from A to B by taking many possible paths. And to take a particular type of a path or a certain path, there is a chance of taking it. So there is a measure that actually tells you what are the chances of taking that path. And so your integral will be a more sophisticated integral. Feynman suggests that if you are taking many, many possible paths with certain chances, instead of calculating energy, you calculate expectation value of the energy. You say, take a stochastic average of the energy over all possibilities. You need to modify your integrand, and you need to modify the space on which you're integrating. So your integrand now will be the previous integrand, which actually tells you measurement of how much energy per length, if you like, per the unit of the path you will be spending, and times some stochastic measure. So I put some stochastic measure in here. So this stochastic measure actually is responsible for telling you what is the chance of taking that path. So it's like a weighted sum. So this is how your integrand is modified. And then your space on which you're integrating is also modified, because you have many possible ways of going from A to B. You integrate over the space of paths. This is roughly really taking a stochastic average. And this is space of all paths is the moduli space of paths. So you would think of, can I come up with a geometrical space, every point of which is a path? If you can come up with that, if this space is nice enough geometrically, you can integrate on it. For instance, it's an integral after all. Is this space compact? If you want to get a deterministic integral in calculus, finite number out of an integral, it better be that the space on which you're integrating is compact. So after you come up with the space of all paths that parameterize all these possibilities, you need to compactify. Otherwise, you cannot hope for getting a number out of this. Okay, so this is basically what we are doing. So this kind of quantum mechanics, right? This is Feynman path integral. Okay, so in a string theory, though, this is again our space-time. Particles are traversing from A to B from all possible paths, right? Let's say you can even have more particles coming together. There are so many ways they can come together. But in string theory, you actually extend dimension of the universe. So extend it. Let me extend it. So let me extend it here. I'm extending it in some extra dimensions. So I can have freedom of adding whatever number of variables that Kate gonna tell me, independent dimensions of my new extended space-time. Maybe I add additional 6 dimensions, for instance. So this is additional 6 dimensions. So base of this manifold, 10-dimensional manifold, is our 4-dimensional space-time, and fibers of it are these additional 6-dimensional spaces. And these additional 6-dimensional spaces turn out eventually, by result of string theories, that they have certain geometric structure. For instance, these additional 6-dimensional spaces are Calabi-Yau manifolds, for instance. This actually was a result of computations. Anyway, so you have extended your space-time into 10 dimensions. You have added these vertical fibers. Everything you do in this new picture needs to be extended. And everything in this new picture is actually extended. So your particles, which are in the space-time, are also extended. Particles are extended as curves, 1-dimensional curves. So this is actually what is happening. Okay, this is what is happening. And all right, now you have these 1-dimensional curves, and they come together. So if you were looking at paths on the base 4-dimensional spacetime, your paths are like curves, right? Because objects in quantum mechanics are like point-like objects. But when you look at them in a space-time, because now your objects themselves have these extensions, you're looking at these loops. Basically, these are the strings. These loops that you add in higher dimensions, these are the strings. So this is exactly what the string is. So obviously, you can actually see yourself with the eye that the path that traversing a loop in the extended space-time gives you is not a curve anymore, it's a tubular surface. So you can kind of connect these things and you will get some picture like this. Okay, so this is in a string theory, the new extended notion of a path. So what does Feynman tell you? Feynman formalism is still valid. Feynman tells you that you are trying to calculate, say, energy or expectation value of the energy, free energy of the strings. The strings can take many possible paths. You take a stochastic average of whatever your suitable integrand is over the space that parameterizes all paths. But now paths in this 10-dimensional extended space are surfaces. In fact, it turns out that these paths are equipped with the Riemannian metric. So these are actually Riemannian surfaces, Riemann surfaces. Okay? So you're integrating some integrand, okay, to calculate the free energy of the system. You're taking some integrand over the space that parameterizes Riemannian surfaces. So space would be family of Riemann surfaces. Riemannian surfaces, or the moduli space of Riemannian surfaces. And where do these Riemannian surfaces live, right? Well, the particles are in a space-time. The strings are embedded in the Calabi-Yau dimensions. The Riemannian surface that you will get, but these are called the string worksheets. These are embedded in the vertical fibers. So the Riemannian surface that you get this way is embedded in the ambient Calabi-Yau manifold. So for the mathematician like me, who doesn't really do quantum mechanics, I don't do quantum mechanics, I don't solve equations of motion, I don't do any of these things, but I understand geometry, right? Question becomes simplified. I have a manifold X, dimension, real dimension 6, so over the real numbers, dimension of this manifold is, say, 6, and I have embedded inside this manifold a Riemannian surface. So let's say it's a surface S, okay? And I would like to calculate this integral. Not only I need to know how many of these surfaces I have, I need to even do calculation of some integrands on them. Okay, so studying the moduli space, the family of these Riemannians over the Calabi-Yau manifold is very important. Okay. Okay. So, all right. So let's actually, this is basically what Gromov-Witten theory is really about. By the way, algebraic geometers work over fields of characteristic 0. Okay. So one of the most famous fields of characteristic 0 is complex numbers. So we work over complex numbers. Complex, theoretically, these Riemannian surfaces would be algebraic curves. Okay, so this guy complex theoretically will be dimension complex dimension 1. That's why I use the notion of a curve C, complex curve C, embedded inside some X. And this X would be a complex threefold. And we are trying to think about, many times we are trying to think about Calabi-Yau manifold. So it could be Calabi-Yau manifold, Calabi-Yau complex threefold, or it could be projective space, let's say P3, it could be C3, it could be anything you want. Okay. Sometimes you need the ambient manifold to be Calabi-Yau, sometimes you don't have this Calabi-Yau property. Okay. Okay. So that's basically what we are doing. Okay. So studying the moduli space of, so what is Gromov-Witten theory about? Gromov-Witten theory is about studying and counting, let's say, studying the moduli space, parameterizing algebraic curves in ambient algebraic varieties, okay, of complex dimension equal to, at least it could be 1, 2, 3, so on and so forth. And mainly, we are interested in counting these curves. Okay, mainly we are interested in counting these curves in the ambient algebraic variety. So you're integrating some function, you would like to calculate energy. If this integrand is 1, in some sense, integral will be somewhat volume of the moduli space. It's like counting, becomes like counting problem. All right. Definitely knowing count these Riemann surfaces in the ambient Calabi-Yau variety or a non-Calabi-Yau variety helps you calculate the energy too. All you need to do if you want to calculate energy, you just need to modify your integrand, put in whatever you want to put in. Okay. Now, why is it this counting even makes sense? This is actually a good question, because you might think, well, how many of these surfaces can I really have? The point is that, as I said in quantum mechanics, your strings and particles can take any path. You can have infinitely many possible paths. Okay? Infinitely many possible paths in your integral. So it might be that you get infinitely many contributions, and that's actually the case. So as you're looking at the moduli space, I'm not gonna call this moduli space of paths or algebraic curves in ambient variety. I call it X, algebraic curve C in ambient variety. I need to kind of do this counting problem in a very controlled way. So let me show you. So let's say I have this ambient space X. I'm drawing a cube because it's easier. I don't know how to draw a Calabi-Yau manifold, I'm sorry. Or even projective 3 space, I don't know how to. But let's say this is X, complex threefold. Okay, for instance, complex threefold. And I would ask myself, how many ways the strings can come together and produce for me Riemann surfaces? Even though there are infinitely many possibilities, you could have a chance of at least classifying them with respect to their topological properties. For instance, you could get a Riemann surface which looks like this. They come together, they separate from each other, some kind of a Riemann surface like that. Okay, so smooth, tubular, something like this. Okay, we are doing mathematics. What are the topological properties of Riemann surfaces? One of them is the genus. So this is a genus 0 Riemann surface. Okay, that's a topological type. There might be infinitely many of such Riemann surfaces in the class of genus 0 Riemann surfaces. They could be deforming to one another or not. And we can look at the component of the moduli space that parameterizes families of genus 0 Riemann surfaces in X. So I'm going to call this component of the moduli space M0. It's parameterizing pictures like this. Okay. Then I can have a component of the moduli space that parameterizes a more exotic type of a Riemann surface. These strings can come together. They can diverge off from each other, come back together, and diverge off from each other, for instance. It's a possibility. So you could have your ambient manifold. You could have a Riemann surface that looks like this, but has a hole in the middle. This is a genus 1 Riemann surface. So there is a component of this whole moduli space parameterizing all possible Riemann surfaces in X that parameterizing this family of Riemann surfaces with this fixed topological characteristic, so on and so forth. So as you can see, one of the things we can do is we can classify this based on genus 0, genus 1, genus 2, genus 3. If you can compute these integrals, you have each component of the moduli space contributes to the final answer for the expectation value of the energy of the system of strings interacting with each other. So you have genus 0 contribution, genus 1 contribution, genus 2 contribution, so on and so forth. Okay. So we are getting very close to the very definition of Gromov-Witten invariants. Gromov-Witten invariants count surfaces in ambient varieties, all right? And they are kind of classified by topological characteristics of these Riemann surfaces. One of them is being genus. The other thing that they are being classified by is that there is more to the topology of this Riemann surface. You could fix the genus, but you can also look at, because this is a submanifold of the ambient variety X, you can look at the homology class of this submanifold, right? So if you have an algebraic curve C with a map, embedding map F into ambient variety X, you can look at the homology fundamental class of C. And I'm not going to tell you what the fundamental class is. It's assumed that majority of the people in this class know about topology, algebraic topology, what is the fundamental cycle. So push forward the fundamental cycle of this curve into the ambient variety would be a homology class. So let's say homology class beta. So you see, beta is one of the other things that I can fix. I can say how many Riemann surfaces of genus 0 I can have in X with fixed homology class beta. Again, turns out many. So this M0, I'm going to decorate it with more data, M0 beta, so M1 beta, and so on. So I fix the homology class, and I get a component. Okay, so this is the second thing I am fixing. Finally, there is another thing that we will be doing, which is, as the Riemann surface is allowed to deform, obviously, many possible ways, it might be that for a given genus and for a given fixed homology class of this Riemann surface, there is still infinitely many of such Riemann surfaces. So the space that parameterizes these things might be somehow that your result of your integral is overcounting these Riemann surfaces. Okay, so you would like to kind of count not exactly single one by one Riemann surfaces, but the representative class of Riemann surfaces. For instance, a given Riemann surface can have automorphisms. So if it has automorphisms, these are just maps. So for instance, you could have a Riemann surface like this, genus 1, right? And it has fixed class. So you have fixed for it the curve class, homology class of the Riemann surface. You have also fixed it. This is the genus is fixed. But then there are so many automorphisms of this thing. So autos. But these basically, these autos. Yes.
Can I ask a question? Is there any math motivation for fixing the class? Because I think in physics you want to have a holonomic class in particular, but I don't know in math what is the motivation.
In math motivation, one of them is actually a consequence of computation. So integral that you define, remember we are doing a very difficult part of mathematics. The space that parameterizes these things is a space that is not as smooth like calculus problems. So we don't have differential forms that we are integrating over this space. This integral, in some way, is an intersection between homology and cohomology classes. So you look at this space, you look at the components of a space, okay, and then you look at homology of the component of this space that parameterizes pictures like this, and you collapse it with an appropriate cohomology class. And that hopefully gives you a number. So it's an intersection theory that we are doing. One of the things in order to make sure that this is space that parameterizes and its homology is well defined is to fix the class actually. Okay. Yeah.
Okay. Thanks.
All right. One other thing is, even if you fix the class, even if you fix the genus, a certain Riemann surface could have many automorphisms, infinitely many copies, isomorphic copies of itself. So it could be different shape. I'm not going to draw the same shape, maybe some different kind of a shape, but all of these are isomorphic copies of this Riemann surface. Well, I need to take into account this thing. I don't want to overcount things. So I would like to count them up to finite automorphisms. I don't want to count infinitely many. It's fine if there are finitely many of them, but it's not fine if there are infinitely many of them. We would like to make sure we would like to count these algebraic curves up to finite automorphisms, up to finite autos. And you might say, what if my algebraic curve doesn't have finite automorphisms? It has infinite automorphisms. Well, then we do something, make sure that it doesn't have infinite automorphisms. We change the curve a little bit. The story is that this curve, as it is deforming and allowed to deform, obvious by the dynamics of the strings, is allowed to deform, it can develop singularities. Okay, so this curve actually can do something which is like the following. So you have the curve, its genus is fixed, but then some parts of the curve can become really, really, really sharp, long, infinite cylinders. Okay, and they become kind of singular. Okay, and it becomes some ugly picture like this. It goes all the way. Okay, like that. So you would like actually to kind of make sure that you kind of keep track of these loci of singularities of the curve. So there is some operation in mathematics that people do. They cut this thing, they cut these regions, and they get a curve over there, and somehow they remember the information of the curve that you get after cutting these parts. And then they actually keep track of basically these points of singularities, these curves of geodesics that you actually get there. And they, instead of counting the curve, they count the curve up to configurations of these geodesics that you get on the boundary of the curve when it becomes singular. So as long as you make sure that there are finitely many of these singular loci after cutting which you get these geodesics, this guarantees that this picture, the algebraic curve, genus one, fixed homology class, with these finitely many pinched locations on it, I'm going to call the pinched locations P1, P2, maybe Pn, and we are going to call them markings. So PIs are called marked points. Okay, then that guarantees that this object will have finite automorphisms. It wouldn't have infinite automorphisms. So if you count how many of such objects in that homology class with that fixed topological type you have, essentially, if you can calculate a number of how many of these you have, then you can just basically say, since this has finite automorphisms, I just mod out by the divide this number, not mod out, divide this number, literally divide by the order of the finite automorphism group. And that's your Gromov-Witten number. So Gromov-Witten number is counting algebraic curves, i.e. Riemann surfaces, with fixed topological type, fixed homology class, fixed genus, and finite automorphisms. Okay, so you wouldn't be surprised if you say that Gromov-Witten number associated to the genus 0 curves is 1/3, right? Because this is very important, right? Because you look at the Gromov-Witten numbers and you say these are counting curves, but then you're looking at rational curves. What does it mean 1/3 of a curve? Shouldn't make sense to you, right? And well, the answer is because these have finite automorphisms and we are counting things up to automorphisms, you get rational numbers out of this calculation. So in some sense, even though they tell you a lot about the space of paths, they tell you a lot about free energy of the string interactions, they are not really enumerative. Because if you tell me I have calculated the number 1/3, how would I know? Is it one curve with automorphism group of 3, or is it 2/6, or is it some other number? So Gromov-Witten numbers are not directly enumerative, even though they tell you a lot about enumerative geometry of X. Counting something in X, that's enumerative geometry of X. Okay, all right, so that's the story of Gromov-Witten numbers. Okay, so we are counting in Gromov-Witten theory. We count in Gromov-Witten theory configurations configurations of curves C together with marked points P1, P2, Pn, which kind of remember the loci where the curve kind of gets singular after certain deformations, together with maps F.
There is a question.
Yeah, go ahead.
Somebody asks if there are no marked points, something special happens.
No, if there are no marked points, as long as your curve is given in a way that having no marked points will induce still finite autos for your curve, it's fine. It's okay to count curves with no markings, as long as your curve, your algebraic curve, has finite automorphisms. Okay, it's totally fine. Yeah. Okay.
But are they rare? I mean, if they don't have marked points, they usually have infinite automorphisms or finite automorphism, or it's not really related?
Well, depends. Actually, turns out that algebraic geometry is something very, it's something very nice, because turns out that these algebraic curves, when you write their even polynomials, beyond genus 1, they actually would always have finite autos, and you don't need markings. Turns out that in order to make sure that you have markings, you need markings, it only as a matter of concern for genus 0 and genus 1. That's it. Genus 0 curve is algebraic curve, genus 0 is like P1. If you look at automorphisms of the projective one space, those are given by Mobius transformations. You can actually see there are infinitely many. I mean, you look at Mobius transformation, A, B, C, D, that gives you 2 by 2 matrices. You look at, actually, there's a group that parameterizes these things, and it's infinite group. As soon as you add at least 3 markings on this Riemann surface of genus 0, you will get finite autos. For genus 1, you will have only 1 markings. But for genus 2 and higher, you don't even need markings. It's always going to be having finite autos. So they are not rare, actually. Yeah. Okay. So this is what it is in Gromov-Witten theory. But remember that, of course, my pleasure. So remember that my discussion today is about super Gromov-Witten invariants. Okay. I couldn't tell you super Gromov-Witten invariants unless I told you what's Gromov-Witten invariants. So this is Gromov-Witten invariants. Okay. So let's now talk about super Gromov-Witten invariants. Okay, here is a definition. So let's now talk about super Gromov-Witten invariants. So we have these Riemann surfaces. So when you do a string theory, it's about string interactions. You get these paths. If you do bosonic string theory, algebra of bosonic fields, and integrals of these over these paths are integrals of fields associated to the strings. If the strings are bosonic strings, algebra of them would be a commutative algebra. So mathematics that you develop for counting these paths will be mathematics of algebraic geometry over commutative algebras. However, if your strings are both bosonic and fermionic, then you realize that the integrals of fields that you have, your fields will have fermionic and bosonic fields. Algebra of bosonic fields is governed by commutative algebras, and algebra of fermionic fields is governed by anti-commutative algebras. As a mix, algebra of integrals of fields, mixed fields, bosonic and fermionic, is governed by supercommutative algebras. Mathematically speaking, for us, this means that all of the pictures that I have put in here in this lecture so far hold is still true, but when you look at the curves, these curves are still embedded in the ambient manifold, but these curves are curves that are written by polynomials in commutative and anti-commutative variables, okay? So this is an extension of doing Gromov-Witten theory. Instead of looking at algebraic curves given by zero sets of polynomials in commutative variables in an ambient variety X, I'm interested in studying space parameterizing algebraic curves given by zero set of polynomials in both commutative and anti-commutative variables. And I'm going to call these curves supercurves. So instead of counting curves in the variety X, I'm going to count supercurves in the variety X. Okay. Now you might say, how is it possible? If you have a supercurve, doesn't it mean X itself should be a super variety? Are you trying to count supercurve in a super variety? No. I'm not trying to do that. I'm trying to count supercurve in a non-super variety. So let me give you some definitions. Here's a definition. So review of J holomorphic curves. J holomorphic holomorphic curves. And then I write a super version of it. Here's the definition. A J holomorphic curve phi from C to X is a map from a Riemann surface C to an almost Kähler manifold. Kähler manifold X with the Kähler form with an almost complex structure. So this J is the almost complex structure on this variety X, such that I want the curve to be algebraic and holomorphic, such that del bar with respect to J of this map phi, which is equal to, by definition, it is 1/2 of d phi plus J times d phi I is equal to 0. Okay, that's what guarantees that the curve after being embedded in the variety X is holomorphic. So this, by the way, this guy is, if you kind of look at it, this is algebraically an element of the space of sections of basically tangent bundle of your C tensored with pullback of the tangent bundle of the variety X. Variety X has a tangent bundle. You can pull it back to curve, and you can tensor it with tangent bundle of the curve itself. If you look at the sections of that bundle that you will get on the curve, the product of the two things looks like these objects. The sections are given by 1/2 d phi plus J d phi I. When the section vanishes, del bar of it vanishes, it basically tells you that anti-holomorphic derivative of this map is going to vanish. So that is exactly what is guaranteeing the curve after being embedded in X is going to be J holomorphic curve with respect to the complex structure of the ambient line. Okay, so Gromov-Witten theory is about, I said about algebraic curves. I'm giving detail about it. It's about counting J holomorphic algebraic curves. Okay, all right. Okay, which means the differential is complex linear with respect to the induced almost complex structure on the tangent bundles of the curve C and variety X. Okay, so this is basically what we had so far. Okay, here is some remark about these J holomorphic curves. remark. J holomorphic curves, for those of you who are in the analytic aspects of studying moduli theory, these J holomorphic curves are absolute minimizers. Minimizers of something called Dirichlet action integral. Do you remember I told you that we are calculating free energy of the string interaction? That is your action integral. Okay, so I have some integral. I never told you why we are looking at J holomorphic curves. You have some integral. It's a Feynman path integral over all possible paths. As a physicist, you would be interested in, this is a free energy of a system. As a physicist, physicists normally are interested in finding what is called vacuum states of the theory. The vacuum states means what are those integrands, fields, which minimize energy? You're interested in optimizers of your integral, energy integral, action integral. Take the derivative of the integral, set it equal to 0. Turns out that the paths that do give you minimization of the energy are exactly J holomorphic curves. Okay. So there are differential equations you get by taking the derivative of that integral. You need to solve. There is a space that parameterizes solutions to those differential equations, and that space is exactly moduli space of J holomorphic curves. Okay. So that's remark 1. Remark 2. Under certain conditions, the moduli space of J holomorphic curves, I'm going to call it now, because of the discussion, M moduli space of M with the index G, genus GJ holomorphic curves with the map to X with the curve class beta, where beta is the image of the homology class of the curve C. So this is the map from C to X. Beta is the image of the homology class. Beta is an element of second homology of X with integral coefficients. Okay, this moduli space is a smooth and non-compact. Remark 2 tells you, as long as you are interested in only parameterizing the smooth curves, you will get a non-compacted space. So if you want to integrate over a non-compacted space, you cannot. You need to compactify. So this picture that I just told you about, these are singular curves. This guy in here is singular. So the story is that you have the moduli space. Interior of the moduli space has these nice, smooth, higher genus, whatever you like, higher genus, if you like, whatever, genus G curves, smooth, and the boundary of the moduli space starts seeing the singular ones. So on the boundary of this moduli space, compactified moduli space, you see the singular curves. Okay? So if you're only parameterizing the smooth curves, it's no use. You cannot calculate any number on it because you need to compactify. So this picture that I just drew in here belongs to the boundary point of the moduli space. Okay? Okay, so that's the second remark. Third remark, the compactified, so okay, let me just say M bar Gn x beta is the compactification of mgx beta. You see, now I have this extra variable n, because this n actually completely tells you how controlled, in a controlled way, how is the locus of singularity of your curve. Okay, as it becomes singular, we are counting in how many points you have those pinched loci, and you need to add this n as a decoration to the, as a label to the term moduli space. So in the interior of this picture, this is mgx beta, the smooth one. As a whole, this whole thing after the boundary, this is m bar gn x beta. In the interior, you don't need n, but in the exterior, you definitely do. And this part in here is the boundary of n bar. Okay, so you have the boundary. Okay, so m bar gn is a compactification of this moduli space of m bar, and whose construction is due to Maxim Kontsevich. It's called moduli space of stable maps. Stable maps. Stable here means that the map f or phi from C to X has finite autos. So Kontsevich says, I have an open locus in the interior, and I would like to integrate over this space. I can choose different boundaries for it. I use the most minimal boundary that this thing sits inside. And on the boundary, I would like to see stable curves with finite automorphisms. So singular, it's fine, but the stability tells you how singular it becomes, okay? You can even extend this boundary of compactification. The farther and farther you go from the center to the boundary, you go farther away even. That means that you're allowing more and more singularity types to the curve. So right now, the curve is kind of singular at points. It might be that you deform the curve so badly that some branch of the curve lies on itself, and you have not just zero-dimensional locus of singularities on each curve, but you can have one-dimensional. That's possible. But that is something that basically gives you the Hilbert scheme. And if you want to do integrals over the Hilbert scheme, you do not compute Gromov-Witten invariants, but you compute Donaldson-Thomas invariants. That's not what we are doing today. Okay. So for now, this is just boundary of this compactification is actually capturing singular curves with the locus of singularity given by points. Okay. Okay. So now you have this, and then part 4, given the compactification, m bar g n x beta, the Gromov-Witten invariants are defined as integrals. So let me tell you how they are defined. Okay, m bar g n x beta, and okay, so a point in here is given by a map from the curve together with n markings to the ambient variety x. Okay, so you can actually have a map from here to n-fold product of x. So this is called evaluation map. What does evaluation map do? If you give me a curve, domain curve with n markings on it, evaluation map takes this system and maps it to phi of P1. Okay, so let me write it in here. Phi of P1, phi of P2, phi of Pn. Okay. This object lives in n-fold product of x with itself. You give me a curve with n markings on it, you map it into the ambient variety x. The map gives you a n points inside x. Okay, so that's the evaluation map. And then here, you can also have the moduli space of only curves. I might not necessarily care about curves after being embedded into the x, but I might just be interested in moduli space of curves Gn. So this is the moduli space of curves. So there are these two natural maps. One of them upstairs is moduli space of curves to X. So it contains the information of mapping to X. Downstairs is just parameterizing curves with finitely many markings on it. And the right-hand map is the evaluation map. So you can define integrals. The Gromov-Witten number is actually given by an integral. So as I told you, when you're calculating the free energy, you might be integrating some integrand. So we are mathematicians, and we know that these integrands could be cohomology classes. So I am gonna pick some cohomology classes in X and pull them back via the evaluation map. So I'm pulling back some cohomology classes in X, let's say alpha n, okay? And I'm integrating them over the moduli space of the stable maps. And these alpha i's are elements of the cohomology of X. These are your integrands. If you are a physicist, you can say these are your fields. This is exactly Feynman path integral. You have integral of fields over this space that parameterizes all paths. Paths are given by stable maps now. Your fields are captured by cohomology classes in the ambient variety X. Any questions? Before I move to the something else. Okay. All right. By the way, the reason I mentioned this moduli of curves is that sometimes this integral can be also realized by the pull back, push forward formula. So pull back, push forward formula. This integral can be realized as an integral on the moduli of just curves, m bar gn. So all you need to do is like pulling back, pushing forward. It's like a Fourier transform. So it could be the same as pi lower star of evaluation upper star of alpha 1 alpha. Still alpha I in the cohomology theory of X. Okay. It could be equal to this sometimes. There are conditions when this is okay, when integration on the top space is equal to the integration of push forward of that class in the bottom space. There are conditions. There are conditions on the degree of cohomology classes alpha I and dimension of moduli spaces that guarantee this identity to hold true, this identity to be true. Okay, so that's basically what it is. All right, this is about Gromov-Witten theory. Now here's a definition. Super Riemann surface. As I said, I want to extend this. If I have fermionic and bosonic fields both, the whole picture will be extended. A super Riemann surface is a complex one, you see? Now I'm not saying one dimensional. I have things over the commutative variables and things over the anti-commutative variables. So I'm now going to have this notion of one dimension. So this is the even degree, even dimension. And this is the odd dimension. One dimensional. Supermanifold C with an odd holomorphic distribution. distribution D, which is the tangent bundle of C. Okay, so let me tell you what this is, such that first I write it and then I explain it, such that 1/2, the Lie bracket, which takes me from D tensor D to TC mod D, is an isomorphism. Okay, let me tell you what is going on here. Distributions, this is about integrable distributions. Distributions are like subvector bundles. Okay? Distributions are subvector bundles. So as a super Riemann surface, the way you should think about super Riemann surface is the following. So take an algebraic curve which is identical to a Riemann surface. This is what we have been studying in the context of Gromov-Witten theory. This algebraic curve is written as the zero set of a polynomial in bunch of ambient variables, commutative variables. Let's say Riemann surface in the Calabi-Yau threefold. Calabi-Yau threefold is a complex threefold. Everything in this threefold is locally described by 3 coordinate variables, right? I'm going to call them X and Y and Z. These are holomorphic coordinates. Okay. So there are polynomials that actually describe the equation of this curve in these coordinates. Okay. So these are going to be our commutative variables. Let me call them now x1, x2, x3, because now I'm going to have more variables, x3, x1, x2, x3. Now, what the super Riemann surface is that it's some kind of odd fattening of the ordinary Riemann surface. So what a super Riemann surface is that it's something that is not only given by polynomials and commutative coordinates, it's also, these are odd directions. It's also given by variables in anti-commuting variables. So this polynomial actually belongs to the ring of polynomials in 3 commutative variables. Now I'm going to extend my ring. So we extend the ring in odd directions. You might ask, how do you do such a thing? It's very easy. You look at the expressions in terms of x1, x2, x3, but this time instead of coefficients with complex C, you pick coefficients from another ring. So I'm going to replace these coefficients with an algebra of some anti-commuting variables, and then think about that algebra as the coefficient system for my commutative variables. So here, these are like, this is the exterior algebra. Exterior algebra of y1 to ym. Okay, here yi times yj is -1 times yj yi. It's very similar to wedging. So similar to yi wedge yj minus yj wedge yi. I think this you have seen, right? In calculus, you have seen it. These are the volume forms and things like that are given by these exterior products. So we have a polynomial ring in some number of commutative variables, this time not with coefficients in C, but with coefficients it themselves in a polynomial ring in anti-commutative variables. Now, if someone asks you, what is it that you expect to see in here? These are expressions in xi and yj's, where yj's are anti-commutative and xi are commutative. Okay? And so this is called the supercommutative algebra. So this is a supercommutative algebra. Remember that if I pick a polynomial in this extended ring, it's not guaranteed that I can always put all the y's on one side and the x's on the other side. It's just completely mixed. I can have x times y plus x cubed plus y squared times x3, you know, it's just completely mixed. Okay. So topologically speaking, when you look at some polynomial in here, I'm going to call this polynomial G now, G. When I have a polynomial in xi and yj's and set it equal to 0, topologically speaking, I get this curve, which is the super curve. And it has in it, if I set all the y variables equal to 0, it has in it the reduced commutative curve. So the reduced structure sits in the core of this super curve, okay? So this is the reduced commutative curve. It's reduced because if I ignore yj's, I will end up with the polynomials only in commutative variables, and that's the curve, okay? If you have some questions about this picture, let me know, okay? But this is what we are trying to do.
Is this like this ring now that you're building is like with Grassmannian variables or something?
Exactly. Like it's the ring of polynomials in commutative variables with coefficients in Grassmannian variables. Now I said 3 in here. There is no need to have 3 x's. In general, our super ring, our super commutative ring is given by lambda y1 to ym, x1 to xn. So the dimension of this ring, the dimension of this, like call it the ring R, the dimension of R, which is given by the number of generators of this ring, is now obviously going to be nm. Right? Okay. All right. So the one that comes on the right-hand side of this line, the dashed line, is going to be the odd representative of the odd dimension. And this is the even dimension. And this is the odd dimension. Okay. So that's basically what that is. So now I told you about this Riemann surface. Now, if I look at what is the distribution, here is what it is. So if I look at let's see the super Riemann surface. If I look at tangent bundle of this curve C, there is a part inside this tangent bundle, right? Because now you can see it yourself. Your curve is given in terms of odd and even variables. The tangent bundle of the curve is parameterizing differentials in terms of both odd and even variables. The odd part is sub-bundle of the whole tangent bundle of the curve, okay? And that odd part is the distribution, okay? So you have this, and this is the odd holomorphic functions, right? These are odd holomorphic distributions. These are things written in terms of differentials with respect to the Grassmannian variables. It sits inside the tangent bundle of C, which sees all the possible differentials of xi and yj. And this sits inside it. Obviously, it's injected. It's an injective map. And then you can take quotient by this injection. This is a sub-bundle of odd holomorphic distributions. And it just turns out that this quotient becomes isomorphic to D tensor D via this Lie bracket structure. So I have a Lie bracket, which actually takes D tensor D to TC mod D. Okay, so that's what it is. Okay. I mean, remember, if you have a bundle, line bundle, tensor product of line bundles is still line bundle. So if you think about even bundle and the odd bundle as being two separate bundles of rank 2, that does make sense still to you that D tensor D could be equal to TC mod D. So I'm just removing the odd one. I look at the odd distributions inside differentials in both xi and yj. I kill the odd distributions. I'm left with even distributions. The Lie bracket, which kind of collapses the odd things together, makes them even. Okay? So the TC mod D is an even distribution, and it is going to be equal to D tensor D. Okay? So D tensor D is also even. Okay. Now in coordinates, let say Z and theta be coordinates in, let's say, C11. Okay, let's do a very, very simple example. Xi and yj, I'm going to call xi z and yj theta. Only one variable, even variable, and one odd variable. So this is even variable. This is the odd variable. Let's just be coordinates of C11. Okay. Then we can define sections of D, the distribution, in this super. So when I say C11, now you should think of C11 as a super curve. How do you say it? You look at the even part, it's a curve. C, affine line. C11 is a super version of the affine line. So it's a super affine line. It sits inside there. Then we can define sections of D, the distribution by, so this D is generated by, I need to give you differentials, right? So this is the differentials. Derivative with respect to theta plus theta times derivative with respect to Z. Everything has now a parity. When things are written with respect to Z, they are even. When things are written with respect to theta, they are odd. D theta is naturally odd. dz is even, but theta times dz is still odd, because odd times even is odd. So sections, which are these derivative operators, are actually given still by odd operators. D theta plus theta dz. This is how the sections of this distribution are defined. Okay. Then D tensor D will become equal to T of C mod.
When you write TZ11, you mean that the even dimension it's 1, right?
Exactly.
But at the same time, you are working in a complex plane like Z or what? I mean, the even part have 2 components or?
No, it means that it's the tangent bundle of something which has an one-dimensional even part, one-dimensional odd part.
So it means that this is not the complex, like Z is not complex. It's just
no, both of them are complex. Everything is complex. They are complex variables, but they have parity with them. Think about this. I give you complex variables x1, x2. Okay.
Yeah.
Under multiplication, algebra of complex numbers is commutative, right? x1 times x2 is equal to x2 times x1. Now, I give you complex variables or functions, differential forms, dx1 and dx2. dx1 is a complex differential form. dx2 is also a complex differential form. Okay? The wedge product of these two things, even though dx1, dx2 are still complex forms, the wedge product is anti-commutative. dx1 wedge dx2 is minus dx2 wedge dx1. So now I'm calling dx1 and dx2 y1 and y2. So now I'm looking at the ring which has x1, x2 and y1, y2. y1, y2 are anti-commuting, but themselves are complex valued functions. x1 and x2 are commuting, but themselves are complex valued variables. Is that making sense?
Yeah, a little bit better. So you mean that from a complex, let's say, plane, you form you form even variables and odd variables, something like
Correct.
that, right?
Absolutely.
Mhm.
Absolutely. Correct.
But the dimension of the even variable, let's say it's 1.
One.
Okay.
Now here it is. Very good questions, by the way, you're asking. C is one-dimensional affine line. Now you can see that because I am picking everything, I'm cooking everything. I see exactly why you are asking these things. You pick things from C, but then you're made of objects, still C-valued objects. You are making this odd algebra. So now you can have C11. What is it? It's a super affine line with the odd dimension equal to 2. What is C12? It's also a super affine line, but the odd dimension is 2. C13 is still a super affine line. Odd dimension is 3, so on and so forth. So as you're looking at the reduced affine line and thicken it in the odd directions, you have the freedom of thickening it with 1 generator, odd generator, 2 generators, 3 generators, any way you want. And all of them would still have this bosonic or the reduced curve sitting in the core. Okay, did I answer your question?
Yeah. Just one more question. So suppose that you have this 1, 2 example. So how many variables, let's say complex variable, will I need to build this kind of tree?
3.
3?
Yeah, 3.
And in general case, for example, NM?
Yeah, NM, exactly. And then in general, for NM, you need to have N plus M many variables.
I see.
Yeah.
Thank you.
So for instance, 1, 2 would be Z and theta 1 and theta 2. Or X and Y1 and Y2. Okay. All right, so this is what that is. And then if I look at this D tensor D, it would be actually, I said that this is via the Lie bracket structure. So 1 over 2, the Lie bracket between two things is taking me from here to TC mod D. Okay, that when I say it this way, it means that if I put in here and if I put in here D, I will actually get something even. So let's just see. D is generated by what I just gave above. So if I take the Lie bracket between this operator and itself, 1/2, I will get, you can calculate, and I will get exactly this. And it's purely even. Purely even differentiator, which is a section of TC mod D, because I have killed the odd part. Okay, so this is what the structure of a super curve is. A super Riemann surface is written in terms of even and odd variables, and then differential theoretically, there is odd distribution of odd differentiators sitting inside the super differentiators, and the quotient is isomorphic to odd differentiators tensor themselves. Okay, all right, so this is what it is. Okay, so that's what that is. Let me see, what am I, so there is this statement, local uniformization. Okay, every super Riemann surface, okay, is locally isomorphic to C11 with its standard super Riemann surface structure. A standard super Riemann surface structure is the one that I just defined above, which is standard super Riemann surface structure defined above. Locally. All algebraic varieties locally are some kind of like manifolds, right? I mean, the manifolds are locally like Cartesian spaces. P1 locally looks like C1 and similar thing. super Riemann surfaces look like locally, like C11. Okay. Okay. A holomorphic map. A holomorphic map. Let me now call it phi tilde, because for Gromov-Witten theory I called it phi. Now I'm going to call it phi tilde from C11 to C is given by, you see, you might ask yourself, how do you map a super curve into a non-super variety, right? I need to answer you this question, right? So this is how you do it. Phi tilde of theta and z, right? Because did I call it z and theta? Yeah, z and theta, I'm sorry. Z, even variable, odd variable, is going to be phi of z plus theta let me see, did I need to give a second map, right? Yeah, phi of z plus theta psi of z. So somehow it's like C11 is like z and theta. Each one of the z and thetas are still complex valued variables, and I'm mapping them both to the C. And I'm making sure that as I'm doing this thing, because C is only even space, I need to make sure that the result is even. Okay, so this psi of z is an odd function, actually.
Can you not do like a projection where you just...
Yeah, that would be just the kind of, then you lose all the information. You don't want to do that. Yeah, you can do it. Yeah. This holomorphic, so I said holomorphic, this is a map. Being holomorphic means, okay, so I need to discuss with you what is holomorphic in this case means. In this case, derivative of this map actually is going to be derivative of psi plus theta dz of phi, something like that. Okay, so this is how you can map a super Riemann surface and a non-super ambient one-dimensional variety. Okay, so that's what it is. Okay, I mentioned affine, super affine line. So now another example is projective affine, projective supercurve, Let me make one example. T11. Yeah.
So what do you mean with that psi? It's odd function, like, yeah. Can you expand on this detail?
Yeah. So you want psi to be kind of, I need to give you maps for psi, but psi is like, you want psi to be an kind of coupling commutative variables with anti-commutative variables. So for instance, psi of z could be z times theta. That's an odd function, right? Because the image, you want image to be an odd variable, odd function in terms of your variables. So z is even and theta is odd. You want psi of z to be an odd function in terms of z and theta.
So, so psi will depend on theta also.
Exactly. It's an odd part of the map. So projective supercurve. Okay, this is the only super Riemann surface of genus 0 by uniformization theorem, by uniformization. So by uniformization, every super Riemann surface looks locally like C11, and the only projective super Riemann surface of genus 0 is P11. It's like P1, which is genus 0, but with an odd direction by uniformization. Yeah. which I didn't mention. Uniformization I didn't mention here, but we don't need it.
Sorry,
Yeah.
coming back to the question, but I still don't understand when you roll this holomorphic map.
Mhm.
You roll phi if you can go up. You roll like the dependent phi z theta. It's equal to, I mean, capital phi. It's equal to small phi of z plus theta. But here, in fact, I see that if phi and psi small depend on theta. So, I mean, it's correct to write
Image could have coupling with theta. Image of it could have theta in it. Image of it. Does it make sense? So phi of x could be x times y, where y is a Grassmannian variable.
So, but then the example you give is like z theta. It's an odd variable.
Which is odd, right?
Yeah, but depend on theta also. So that's my point. Like, in fact, if we, it seems that we have to write like phi z and theta, and also for psi z theta.
I see. Yeah, that's correct. That's fine. Yeah.
But if I roll this, for example, if I take this example, psi equal to z theta, then it's just zero. This odd part, because theta squared is zero.
Yeah, that's correct. So yeah, I see what you're saying. If I need to write it like this, and then I need to kind of call these even and odd functions, maybe. Yeah. This is the fix for it.
Yeah, but now the other question that arises, just like if I just take example, let's say this example z theta, and I just put plug in this equation, as I see that this odd part vanish. So that's my question now. So it's, I mean, the question is what exactly is it's psi? It's odd part, but how it's
not vanishing. Why should it vanish? Why should it vanish? Why should it vanish?
Because for example, in this specific example, you have z theta, right? Psi is equal to z theta. Just an example. And you put there, and you get theta times z theta, and then you can commute this.
No, okay.
And you get in this second term, you get theta squared, which is zero.
Yeah, you're right. There's a certain problem with this one. In this part, it actually does vanish. You're right.
Yeah.
Yeah, correct. Okay, let me fix this later. You're right. I agree with you. Okay, very good. Yeah. Let me fix this later, because I'm kind of running out of time, but let's come back to this later. Okay, yeah, but I got what you're saying. I will fix it for you. Okay. So what is it? I want to get to the main point of the discussion. So these are the only genus zero supercurves by uniformization. Now let's see. So we would like to. So now we would like to study supercurves in families. Okay. So let's just see how I want to do it. So I have a supercurve C mapped to ambient variety X. And I would like to think of this reduced part of this sitting inside it. So this is the one that is given by only the vanishing of the commutative variables, and this is supercommutative. Okay. So the way you would like to actually think of these as families is that by looking at parameterizing the spaces. So consider an even and odd parameterizing scheme B. So this could be spectrum of something like what we had before, y1 to ym, x1 to xn, something like that. Okay, would be the spectrum of this guy. And then the family, then the B family of super curves is given by basically something like C tensor with B over the underlying curve. So this is over the ground field, say C M N. Okay, so this is how you can define the notion of families of super curves. So the point is that similar to commutative algebraic geometry, if you have some curve, let's say some curve with an ambient, with a map to an ambient variety, what you can do is you can pick a parameterizing the scheme S. For instance, you can pick affine line if you want, or some n-dimensional affine space, and then you can look at the family, which is S to the AN times X, something like that. So basically the way you do it is that the correct way of really writing is the following. So you have AN to the underlying ground field. So a spectrum of the underlying ground field for us is going to be complex numbers. And you have X, which is also a variety over complex numbers. Then over here, you're looking at AN times X, and your family actually lies on top of this thing. So let's say your family is called, let's call it something, C over X times AN. Okay, so what it does is that for every point of the AN, it actually gives you one of these maps from the curve into the X. That's what the family does. Here we do the same thing, except the ring or the scheme that we are picking for doing the parameterization is a scheme or ring over both commutative and anti-commutative variables. Okay, so this is what it is. Okay, did I explain this part correctly? Because I need to go a little bit faster. Is it okay, this one? Any questions? Okay, good. All right. All right. So let's actually discuss about these moduli theories over this. So by the way, here's a definition. Here's a definition. Due to Kähler and myself and Yao, which is 2021. Let C be a super Riemann surface and XWJ an almost Kähler manifold. Almost Kähler manifold. Okay, a map phi tilde from the super curve. So I'm going to put index S if you like. So C super Riemann. So C super to X is called a super J holomorphic curve if similar to holomorphic curves that you're looking at, this tangent sections of the tangent bundle of the curve tensored with the pullback of the tangent bundle of X. Remember, so you have a curve embedded into X, you look at tangent bundle of the X, pull it back to curve, tensor it with the tangent bundle of the curve. You look at sections. You want to make sure that the anti-holomorphic derivatives vanish. Similar to that exactly happens for the supercurve. So you have the map from supercurve to X, and for this map, you can actually define certain similar differential equations. So you have d bar of phi tilde, which is exactly going to be 1/2 d of phi tilde plus j times d phi tilde I, restricted to D. So now tangent bundle of the curve has the even and odd distributions, and I can restrict to the odd part, and I would like that to be equal to 0. This is the differential equation. This is the analog of equation, which I just defined here for J holomorphic curves. Let me show you. This equation here. So del bar operator of the map phi should vanish, and that gives you the J holomorphic curve. So similar situation in here, except now our differentials and distributions have both even and odd parts. Okay, so we gave this definition. And okay, I can define this derivative in terms of coordinates. So example, super, let's go here, super J holomorphic curves, C11 times B to Cn. You see? Now I'm calling the curves because I'm interested in family of curves. Okay, so I pick this even and odd ring, or scheme over an even and odd ring, and the family for me would be C11 times B with a map to Cn. What does that mean? It means that if you restrict to a geometric point of B, you will get one of the supercurves which are being mapped to the affine n-dimensional space. Okay, so this is an example, of course. Okay, so let's write it down. So let theta and z again be the super variables, super coordinates.
There is a question on the chat.
Yeah, what is the question? I didn't see it.
What is an almost Kähler manifold? Kähler manifold, all of them have almost complex structure. No?
That's right. That's exactly what we mean. Yeah. It's exactly almost, yeah, Kähler manifold, basically. That's what we mean. Let theta z be the coordinates on C11. And lambda alpha be coordinates on B. And z of B complex coordinates on Cn. So now I have three spaces. I have C11 with its super coordinates, I have B with its own coordinates, and I have the coordinates of CNN. And I have this differential equation, vanishing of which gives me the notion of super J holomorphic curve. Okay, so the differential equation can actually be given this way. So the map phi tilde from C11 times B to Cn can be written in coordinates as B. Remember that we are sending things into Cn. So image of the map phi tilde in Cn has n components. And I've picked index of the components of Cn B. I'm not calling them Z1 to Zn. I call Zn, I will call them Zb. Okay. So the bth component of phi tilde would be exactly phi b of z bar lambda plus theta psi b z bar lambda plus theta psi b. These bars are the anti-holomorphic, the conjugation. So this is conjugation, conjugation. Okay, theta bar of z bar lambda plus theta bar of b z bar lambda. Anyway, this is what it is. The map is then the map phi tilde is J holomorphic, is super J holomorphic if, well, you need to just expand this differential equation. So it would be d theta bar plus theta bar dz bar, which is the thing with respect to anti-holomorphic super coordinates, of the bth component of phi b needs to vanish. So this would be psi bar b of zz bar lambda minus theta phi b of zz bar lambda plus theta bar dz bar phi b of, okay, anyways, I mean, I'm just putting it here for the sake of completeness. It's a long expression. This you want to vanish. Okay, so it's a complicated differential equation, okay? But anyways, nevertheless, this is exactly what we are getting. Now, I would have, it's 11:40 Boston time. I have 20 minutes. So let me tell you, how do we count these things? Okay, so in usual Gromov-Witten theory, you're looking at a basis space with a bundle on it. So this space is the moduli space of stable maps, actually. So this is the moduli space of genus G X stable maps. All maps from the curves into the ambient variety. There is a bundle on it. This is a vector bundle whose sections are actually given by sections of which, so section, let me draw for you a section. This is a section of this bundle. Let me call this bundle V. Oops. Okay, so this section belongs to the section over the space like that. And the fibers of this section, if I look at the fibers of this this bundle over this vector bundle over every point of the moduli space is a map from the curve into the ambient variety, curved together with a bunch of mark points. The fibers of this vector bundle are exactly the anti-holomorphic derivative of the map. So if you're interested in counting J holomorphic curves embedded into X, you would be counting the zero locus of this section. That's exactly where the anti-holomorphic derivative vanishes. So in the loci like this exactly the point that where the section meets the zero section of this bundle, this is exactly a F from C to X where C is J holomorphic. This is exactly what we are gonna do in here. Here, we have similar thing. We are looking at the moduli space of all super Riemann surfaces into X. We look at the super bundle with a section. And the fibers of this vector bundle over every point of the moduli space, which is a mapping from a super curve into X, is actually given by this D bar that I just defined, D bar of the map. So if I'm interested in looking at super J holomorphic curves, I need to be looking at the zero locus of this section. And this section is, again, section of this bundle over M, and I'm gonna call it super bundle, okay? So the reason that these invariants are called intersection numbers is this exactly. It's a bundle, and the intersection number is exactly the count of intersection points of the section of this bundle, which is cooked up precisely this way with the zero section of the bundle, which is the space parameterizing all possible maps into the ambient variety. Okay, so this is what we are doing. Okay, so let me actually tell you the result of this calculation. So any questions about this picture, by the way? Okay, given let's see, the differential equation D bar J of phi tilde equal to 0, okay, we define a moduli space, the moduli space of super J holomorphic curves as an intersection of a section of a bundle, so as an intersection of S, which belongs to section of a bundle over the moduli space of all maps from Riemann, super Riemann surfaces into X, where E restricted to a particular map from the super Riemann surface into X is actually given by space of sections of the dual of the distribution times phi tilde pullback of Tx tensor with O of C. Okay, so this is a map phi tilde. It's mapping CS to X. The bundle, this has to do actually with looking at the very description of this map. Okay, so this guy that I have defined in here is giving me a section of a bundle. The way I construct this bundle, I need to make sure that this bundle, fibers of this bundles are given by these differential operators. So what bundle it would be? It should see d phi tilde. And now d phi tilde sees the distribution and sees the differential in the commutative variables, basically. And if you work it out, this bundle exactly would be this. It will see the odd part, but the dual of odd part. So this is distribution D that I have in here. And it will see also derivatives in terms of the ambient variables. So it would be pullback of Tx, okay? Derivatives in terms of coordinates of the ambient variety, okay? Here C is the reduced or commutative, is the commutative or reduced part of CS. So C is the one that sits inside CS as the reduced underlying core curve in the core. Okay, so this is what it is. Now I have this bundle. So this is my bundle that I just defined this way. This is my moduli space of all maps from C to X. And this section, this is your section. And the zero locus of this section gives me the moduli space of super moduli space of J holomorphic curves. So I'm going to put some J in here that sit inside this bundle. And this is essentially the zero locus of this section. Okay, this is basically what it is. Okay, I am looking at points. I mean, you shouldn't be fooled by the way or misled by the picture I'm drawing in here. It's more than just points, okay? These are loci. There are loci where this section actually vanishes. There's an infinite dimensional vector bundle, a vector bundle whose fibers are infinite dimensional. That's your vector bundle E with a section. The zero locus, vanishing locus of this section itself is the moduli space of J holomorphic curves that sits inside moduli space of all possible maps from S. So, okay, so this is sitting inside the moduli space of all possible maps from super Riemann surface into the ambient X. Okay. Okay, good. Now, let me tell you a little bit about properties of this moduli space. So this moduli space, this Z of S, which is my moduli space X beta sitting inside moduli space of all maps. This is a submanifold, is a super, actually not a manifold, super subscheme of, oops, what happened? Did I lose us?
No, you're still here. It's just the
Okay. Oops. Oh, sorry. I don't know what happened. Is a super subscheme of dimension. Here's the dimension of it. Dimension 2 times dimension of x over complex numbers minus 2 times C1 of Tx over the class beta, and odd dimension 2 times C1 of Tx over class beta. It's a super moduli space. Okay, it's the moduli space parameterizing super Riemann surfaces mapped to the ambient variety such that if I look at the even part of the Riemann surface, its homology class is equal to beta. You should remember the super Riemann surface has a topological characteristic similar to Gromov-Witten theory. There is no super cohomology class. The way we parameterize these things is, as I said, C11 is a super affine line. C12 is also super affine line. C13 is also super affine line. Topology of the reduced curve is still topology of affine line. So the way we distinguish between super curves is basically topological core of the super curve, which is the commutative curve, associated to which you have the homology classes, cohomology classes, everything, together with the odd functions, which gives you fattening of this commutative curve into the odd directions. So when I say beta in here, this beta is still an element of homology of x with integral coefficients. I'm not putting super homology in here, remember that. This beta is just here beta is equal, by definition, is equal to homology class, okay, of curve C. So homology class of F star phi lower star of homology class of C. Maybe I call it C reduced, where C reduced is the one that sits inside C, and C is being mapped to X. You see, so I embed this C reduced, and this is my map phi tilde, and I actually look at composition of these two injection, and then this is fundamental class of the image, the reduced part of the curve into the ambient variety, okay? The dimension of the moduli space depends on dimension of the ambient variety and the fundamental class of the bosonic part of the supergroup, okay? All right, so this is what it is. And then there is lots of detail I wanted to discuss about, but to tell you how the Gromov-Witten invariants are actually defined here, the notion of super Gromov-Witten invariant is the following. It turns out that the moduli space M bar Gn x beta sits as a bosonic component, bosonic, i.e. commutative, i.e. reduced component inside the moduli space M bar super Gn x beta of super stable maps. Okay, so you have basically, this is what we are doing in here. You have M bar G n of x beta. I'm going to put an index reduced in here. This is Konsevich's moduli space, actually. This thing sits as a sub-scheme or substack inside the super moduli space of superstable maps. So here the points are maps from a curve with n markings into the ambient variety X. Here the points are maps from a supercurve, again with n marking to the ambient variety X. This is J holomorphic curve. This is super J holomorphic curve. This moduli space M bar Gn X beta is obtained by compactifying the zero locus of section of a bundle whose fibers are antiderivative of the map F. So you took at the antiderivative, that gives you J holomorphic curves, that gives you open locus, then you compactify. Same thing in here. You have the map from phi tilde to X. There is an infinite dimensional bundle whose sections or fibers are given by anti-holomorphic derivatives of phi tilde rather. Look at the zero locus, you get mgnx beta, the super version of it, and then you compactify. The compactification M bar Gn of Kontsevich sits inside the super compactified moduli space. Okay. Now, why is this actually useful? I tell you why it is useful in the last 4 minutes. It is useful because of the following. So here is my moduli space of super guys. Okay. Inside this moduli space, I have moduli space, the reduced moduli space, or the Kontsevich moduli space. Now, the way we do calculation is the following. In order to do calculations, we actually show that there is a torus acting on this moduli space. We prove that there exists a torus T acting on the moduli space whose fixed locus is given by precisely M bar Gn X beta. If I give you Cn, there is this torus C star n acting on Cn, right? So for every component of Cn, the variables that local chart of Cn, x1 to xn, I can pick a torus given by n tuple of non-zero complex numbers, t1 to tn, that actually act on this thing, star. It will give me t1 x1, tn xn. This is the action of the natural torus on Cn. Now, if I give you Cnm, I can actually define a torus action that is only scaling the odd directions. I can do that. So I can see that there is a torus C star to the M that acts on it. And it's like T1 to Tm acting on X1 to Xn, Y1 to Ym, given to X1 to Xn, T1 Y1, Tm Ym. If someone asks you what is the fixed locus of this torus, obviously the part that doesn't move by the action of this torus is the bosonic part, right? The commutative part. So fixed locus is exactly equal to x1, xn, that's the fixed locus. Essentially, the trick of the computation of super Gromov-Witten invariants is exactly coming up with a natural torus acting on the moduli space that is scaling the odd fibers of the supercurves, but not the bosonic curve. As soon as we do that, we realize that we can prove that the fixed locus of this torus action is exactly the reduced moduli space of the stable maps that sits inside it. After we prove such a thing, the calculation becomes much easier. So all you need to do, you need to basically see that this fixed locus has a normal sheaf. So there is a normal sheaf, or if you like, normal bundle. but it's not going to be a bundle, unfortunately. It's a sheaf. It's a normal sheaf that captures deformations outside of the torus fixed locus, which is the reduced moduli space, into the super moduli space. So when you define your notion of invariance, you basically can show that your integral can be given as an integral over the reduced moduli space. So let me just write it like this. So before we had m bar gn x beta evaluation map x to the n and the moduli space of curves, and the Gromov-Witten number was given by an integral over the m bar gn x beta evaluation upper star of alpha 1 up to alpha n. Okay. Now the super Gromov-Witten invariant is actually given by summing over m bar super gn x beta evaluation alpha 1 to alpha n, which turns out to be exactly equal to an integral over the reduced moduli space, which is the torus fixed locus, where the integrand needs to be normalized. So this is called localization theorem. You normalize by looking at this torus fixed locus and what is the contribution of these normal directions. So that's a sheaf. You put it in here. And you take the Euler class of this sheaf. So it's again, Euler class is a cohomology class. It's again cohomology classes. You get modified by dividing by the Euler class of the normal bundle to the original moduli space. This is the only possible way you can actually define the notion of super Gromov-Witten invariance. Why? Because if you wanted to define this integral right here using your normal intersection theory, you actually need to study super cohomology ring of the moduli space or super Chow cohomology. The problem is that super Chow cohomology doesn't exist. Okay, so the reason this is called, this statement, this identity is called localization. Localization with respect to a torus action. To a torus action. And the reason we need to localize and write integrals over m bar gn x beta is that in intersection theory over the superversion is not well defined due to lack of a well-behaved super Chow cohomology theory. Super cohomology, or if you want to really be precise, super Chow cohomology, due to lack of a well-behaved super Chow cohomology theory over m bar super gn x beta. Okay, all right. I actually wanted to go through the proof and kind of, it's very interesting how this normal sheaf actually works out. This normal sheaf, what is it capturing? I wanted to actually put for you some of the, there is a kind of, this normal sheaf, by the way, this normal sheaf understands deformations. You see, what does the normal bundles do here? On the interior, on this moduli space, the reduced moduli space, you have stable maps. And if you want to deform them, it actually tells you how far the superstable map is due to having odd coordinates from the stable map itself. So this normal shift understands deformations in the odd directions. There is an object in the derived category of the moduli space whose cohomology gives you exactly this normal shift. I wanted to write for you a little bit about the derived categorical properties of the moduli space of superstable maps. I wanted to write for you derived categorical properties of moduli space of stable maps. And I wanted to compare these two derived categorical things and show you what's the discrepancy between the two. It's an object, and cohomology of this object gives you this normal sheaf. Okay. Nevertheless, I think this is good enough for now because anyways, so you calculate what this normal sheaf is, and it is pretty much done computationally as well. And your final integral is going to be everything you had before, but modified. So you pull back homology classes from X, your integrand, you divide by the Euler class of this normal sheaf, and then you integrate still over the Kontsevich moduli space. Intersection theory over supermoduli space using supercohomology theory is not even well defined, doesn't exist. This notion doesn't exist. So if you want to hope to calculate super Gromov-Witten invariants, I think one easy shortcut is actually to do what I just elaborated here, to using localization and reduce the integration over the reduced moduli. Okay. All right. Any questions about these parts?
I have a little question. Why do you choose a torus?
Well, this is one of the ways of calculation. So there is here is how you can do it. So this is a classical story. So let me write it for you here. Here, classical story is called Atiyah-Butt localization. Atiyah-Butt localization. It's a very nice and neat result. You have a space X, and you have a group, space with a group acting on it. Doesn't need to be torus. A group acting on it. And then you actually look at the fixed locus of this space under the action of the group. Okay. So it might be that the fixed locus is several components. So G fixed locus 1, G fixed locus 2, up to G fixed locus n, for instance. Okay. Several components. Each locus has a normal bundle inside the ambient space. So normal bundle 1, normal bundle 2, normal bundle n. Okay. Atiyah-Butt localization tells you that the fundamental class of this space X is actually written in terms of the fundamental classes of the G fixed loci of X. So it's a sum from 1 to n of fundamental classes of Xi, G fixed locus of Xi, divided by Euler class of the normal bundle I. This is what it is. So if you want to integrate these integrals, as I mentioned, we do algebraic geometry. In algebraic geometry, we don't have integral. We have homology and homology classes collapse together. So if you're integrating something, some alpha over X, intersection theory tells you that this alpha should be an element of homology of X. Fundamental class of X is an element of homology of X. And integration means collapsing homology with homology. Okay. So this alpha is integral of alpha is basically alpha capped with fundamental class of X. So now if your G fixed loci are easier to understand, then alpha captured with this one will be alpha captured with the sum of Xig divided by Euler class of normal bundle of I. That's what it is. And that's exactly summing over I of integral of alpha divided by Euler class of Ni over Xig. This is the result of Atiyah and Butt. Okay. Now remember, fundamental class makes sense in differential topology for a smooth space. Moduli spaces we are looking at are not by any means as smooth. They are singular, they are ugly, they have multi-components, which are not even equidimensional. If I asked you what's the fundamental class of a line, you will say it's a class of a line. What's the fundamental class of a space, which is the union of a point and a line? What is it? It's not well defined. So in algebraic geometry, we have extended this notion of fundamental class to something we call virtual fundamental class. Okay, so the statement that we are using in here is that this integral, so when we say integral of some class alpha over m bar gn x beta, this space is not well defined. It's a superstack, and it has many, many components, not equidimensional. This is alpha intersected with what is called virtual fundamental class of the moduli space. I didn't go to the virtual class theory because it takes 4 sessions to actually talk about how to construct this virtual cycle. Why is it called virtual? Yeah, it is actually virtual. Okay, it's some class which sits in the homology theory of the moduli space. Homology theory of the moduli space is a graded ring, and the degree at which this class lives in is exactly equal to the expected dimension of the moduli space. Okay, anyways, I didn't talk about it, but this is what it is. And this result of localization that we have proved with Kähler and Yao actually tells you that this alpha intersected with this virtual class of the supermoduli space is the sum over I of alpha intersected with normal moduli space, reduced moduli space, divided by Euler class of the normal sheaf Ni. Now, each one of these intersections with the Kontsevich moduli space have been studied a lot in the context of Gromov-Witten theory. I mean, integration over the Kontsevich moduli space is now you can say almost semi-classical literature. So the way you can define notion of super Gromov-Witten invariance is to turn the problem into an integral over Kontsevich moduli space and then use formalism there to calculate. All you need to do, you kind of need to see how your integrals get modified when you're bringing these extra contributions from normal sheaf into the picture. Okay. Yeah, sorry, I went a bit slow in the beginning because I wanted to give you a picture, but now I went a bit fast in the end. But I hope that you kind of learned a little bit of flavor of what we are doing in here.
No, it's okay. Thank you very much. Yes, thanks, Artan.
Thank you, guys.
Is there any question?